although this is a device that will be more interested in an AC context, I think it makes sense to introduce inductors in a DC context. So I'll start with that. Officially, the name of the phenomenon is self-inductance, but almost everybody drops saying the self part most of the time. This is to distinguish it from mutual inductance, which is how a transformer operates. Anyway, I'd like to start by just thinking about, I have some battery here on something that gives me an EMF, a DC EMF at the moment. And then I'm going to stick here a variable resistor. Now, in electrical circuit diagrams, anytime you put an arrow through the device, it means make it variable. So this means I can literally turn a knob and change the value of the resistance. And then this is going to go through our inductor, which remember is literally just a loop of wire. Often it's wound around an iron core or something like that. The symbol for inductance is L. Okay, so let's just say that I've got this dialed up to a pretty hefty resistance. Not infinite, but just some big number. What that means is that we'll be running a current through the circuit like so, clockwise. Like that. All right. Now, the thought experiment I want you to go through is I want you to first think about just plain what will happen to the current in the circuit if I decrease the resistance. So I'll just literally turn the knob from the higher resistance it's currently at down to some lower value. So if I drop the resistance, what's that going to do to the current through the circuit? Yeah. By Ohm's law here, if I drop the resistance, we're going to get an increase in the current. Now, the inductor is going to have something to say about how fast that current increases. And this is because if the current goes up, what is happening to the magnetic flux inside our inductor? Yeah, it's also going up because this is a solenoid, and the magnetic field strength of a solenoid is proportional to the current. We're not changing the shape of it. So if the current goes up, the magnetic flux goes up. So what this means is that by Faraday's law of induction, we will induce an EMF in the inductor. Induce an EMF. There we go. And in order to make sure that we don't create a perpetual motion machine of the first kind, a machine that can run forever and do work, we will need it to be such that the polarity of the induced EMF is such that it will oppose the change in current. If the polarity were the other way, what would happen is as I decreased my current, then effectively the inductor would be turning into like another battery, which would increase the current, which would induce more EMF, which would increase the current, and you'd have something that could run forever and do work, which is a perpetual motion machine of the first kind. So the inductor, the polarity of the induced EMF has to be such as to oppose the change in the current. This is sometimes known as a back EMF. All right, so with that, we can go ahead and start to define inductance. which is a electrical property of the device. So let's think about it as a solenoid, let's say. I go ahead, run a current through my solenoid like so. I'm going to make a magnetic field going through. All right. Now, we will define the inductance to be the number of turns in the coil times the magnetic flux going through the coil. So that will be the magnetic field strength times the area of the coil. So basically the number of magnetic field lines over the current. Now, this combination of the number of turns and the magnetic flux, this product, it actually gets its own name. It gets called the flux linkage. I've never seen a standalone symbol for it. I'm sure electrical engineers have a symbol for it. I just haven't seen it. And so, if we go and look at Faraday's law of induction, and here we'll take careful care of our plus and minus signs, the induced EMF by Faraday's law will have to be minus the number of turns times the, it's a terrible delta, there we go, times the time rate of change of the magnetic flux. That's just Faraday's law of induction. This will be the voltage difference across my inductor. Now, one thing I can do is I can say that, hey, N times the change in phi b would be the same thing as the change in the product of N and phi b. So with that thought, I can write this as minus the change in N times phi b, our flux linkage, over time. Now, if I take this and multiply both sides by I can say, hey, that is minus the change in the inductance times the current with respect to time. Now, the inductance is going to be dependent only on the details of how this is built, because it's the flux linkage per unit current. Everything else, so what goes into the flux linkage? Well, the number of turns, that's never going to change in our device. The magnetic flux will always be directly proportional to the current, because no matter what kind of shape this is, that's how the equations for magnetic field strength always work out. It's always directly proportional to the current. And then you can have some other factors in here relating to the details of construction, but again, the details of construction won't change. So all of this here is going to be a number that is specific to the device and won't change. Because that's the case, I can say the change in the product of L and I, since L never changes, will be equal to L times the change in I. And I can finally write it that the voltage across the inductor will be minus L times the time rate of change of the current going through the inductor. Now, this inductance here does have a unit. It's named after the American physicist Joseph Henry, who also was a director of the Smithsonian at one point. So it's the Henry. You can follow through. You can say it's either 1 volt second per amp, and you can rework that to say it's an ohm second. All right. So just to make this kind of concrete for our DC case here, let's just imagine that I have a 3.2 millihenry inductor That's a good typical value, is in the millihenry range. And let's go ahead and say that our current through the inductor we'll let max out at 4 amps. Let's say for the first 2 seconds, the current rises uniformly from 0 to 4 amps. And then over the next 3 seconds, so from 2 to 5 seconds here, we'll say the current through the inductor stays a constant. And then over the next 4 seconds after that, so from 5 to 9, we'll say that the current decreases back down to 0 uniformly. And what I would like to plot is the voltage across the inductor as a function of time. So to get that, what we can say is, okay, this is the voltage across the inductor is minus L times the time rate of change of the current. So this will be at whatever point we're interested in. This will be equal to the slope of our I versus T graph here. So here in this first segment, we'll be breaking this into 3 segments here. So in segment number 1, the slope here, well, we've got a rise of 4 amps and a run of 2 seconds for a 2 amp per second slope. Here in segment 2, it's a flat line. The voltage never changes, so the slope will be 0 amps per second. Then here in segment 3, my slope will again be the rise over the run. Now here my rise is negative 4 amps and my run is 4 seconds. So my slope is minus 1 amp per second. Okay. So that means that the voltage across the inductor in segment number 1, that'll be equal to minus L, don't forget that minus sign, times the time rate of change of the current. So this will be minus, I'm just going to leave it as millihenries, why not? 3.2 millihenries times 2 amps per second. All right, so this will, when you do the unit analysis, a henry times an amp divided by a second is a volt, and let's just leave the milli there. You're allowed to do that. Remember, milli is just an instruction to multiply something by 10 to the negative 3. So we can say that we have a negative 6.4 millivolt change in voltage across the inductor. Now, by the same token, in segment 2, that would be minus 3.2 millihenries times 0 amps per second, so 0 millivolts. And in segment 3, there'll be minus 3.2 millihenries times negative 1 amp per second. So this will be plus 3.2 millivolts. So if I want to plot this, so here we go. We'll say this is the voltage across the inductor in millivolts. I'm just going to use a really jacked scale here and just say this is minus 6.4 minus 3.2 plus 3.2 plus 6.4 millivolts to 5.9, trying to keep it linear there. And so then my graph is just going to look something like this. Now, real world, you're not going to have these jump discontinuities. Real world, this will curve a little bit. It's sort of a sigmoid shape, it gets called, but we can idealize here. All right. Now, just to give some sense of how the details of construction feed into finding the into the inductance of a device. Let's just say you have a solenoid. Let's just say it's an air core solenoid. So if I make an inductor out of a solenoid, which is a very typical shape, either a straight line solenoid or a toroidal one, donut shaped, we'll do a straight line one here. So magnetic field, we've seen before, the magnetic field strength of a solenoid is mu naught times the number of turns over the length of the solenoid times the current. All right. Now, what I'm going to want in order to get the inductance is I'm going to calculate what the flux linkage would be. So the flux linkage would be the number of turns times the magnetic flux. Well, the magnetic flux will be the magnetic field strength, because in a solenoid, the magnetic field strength is pretty much constant, times the cross-sectional area of our solenoid. Okay, if I put in the magnetic field strength here, I get mu naught n squared over L I A. And my inductance, by definition, is the flux linkage per current. So that's just going to be dividing this current out here. So that's going to give me mu naught n squared over L A. So what we get out of this is that my inductance actually goes as the square of the number of windings. That might seem counterintuitive at first, but remember, every time I put in a winding, I increase the amount of magnetic field, I increase the strength of my magnetic field, but also I have basically created one more pickup coil to for Faraday's law of induction to work. So I both strengthened the magnetic field and I also enhanced my ability to induce an EMF, both by a factor of n. And otherwise, the bigger the cross-sectional area of the solenoid, the bigger the inductance, the shorter the length, the bigger the inductance. Alrighty, so now that we've done that, now let's go ahead and actually start thinking about this in AC. So I'm going to introduce the inductive reactance. So at the moment I'm going to think of just a purely inductive circuit. So now I have an AC EMF source, and I'm going to hook it purely across an inductor like so. So here we can kind of start to think at least what the limits would look like with regard to frequency. So we can think about what our inductive reactance might have to look like. So in the limit of the frequency being 0, that's DC. That means that our time rate of change of current is 0 because you're not changing. So the voltage across the inductor would have to be 0. So this means I would need my inductive reactance to be 0. It approaches 0 as frequency approaches 0. On the other hand, if I let my frequency get big, then what's happening is the current is changing super duper rapidly. The faster I oscillate back and forth, the more quickly the rate at which my current is changing. So that my time rate of change of current would also be big. So that means that I would need the voltage across my inductor to also be big. Now, to do a thorough analysis of this would involve the methods of calculus. And so I'm just going to go ahead and quote the result. So in analogy to how we defined capacitive reactance, we can define an inductive reactance. And we will say that it is equal to 2 pi FL. As before, the units of this will be ohms. And once again, this is not a resistance, it's a reactance. It's just reacting to the fact that the current is changing. So again, I like to call this an R-like quantity. It has units of ohms. It has something to say about how big the current can be in the circuit. But it's not going, we don't dissipate energy. We temporarily store it in the magnetic field, and then we extract that energy back out from the magnetic field in an oscillating manner. So again, in analogy to what we did with capacitive reactance, we can say that both the RMS and peak voltages across the inductor will be equal to the corresponding RMS or peak current through the inductor times the inductive reactance. So this will work for RMS or peak. There is, again, a 90-degree phase difference for the instantaneous value. We'll get to the... So let's go ahead and start to think about that for a hot second. So the deal here is, again, if we go back, what Faraday's law of induction is going to require instantaneously So thinking of it as a function of time, so that's our lowercase notation. The voltage across the inductor by Faraday's law of induction will be minus L times the time rate of change of the current. So this is similar to what we were worried about with capacitors, except that with capacitors, this was a charge. A current is already a time rate of change of a charge, and then this is the time rate of change of that. But it's still the same kind of logic. Again, I'll just go ahead and cite that using the methods of calculus, we can get that if, say, our applied EMF, so here we'll make green my applied EMF. We've been going with that being a cosine. For our instantaneous current, it will wind up looking 90 degrees out of phase. Now this isn't the exact same thing as with the capacitor. Here, it is again a 90-degree phase difference like before, but now the difference is that the current lags the voltage by 90 degrees. With the capacitor, the current led the voltage by 90 degrees. So what I'm meaning by that here is that, say here, if I come to a peak of voltage first, then a quarter of a period later, or 90 degrees, a quarter of a period later, I'll hit that peak in the current. Or say here, as I'm crossing 0 volts on the downswing, a quarter of a period later, the current will cross 0 amps on the downswing, and so forth. So this is the opposite. With capacitors, you would see the feature happen on the current first, and then the voltage. Here you see the feature on the voltage first, and then the current. So you say that the current lags the voltage by 90 degrees. So let me just give you a quick mnemonic for how to remember that. The mnemonic goes to always remember your friend, Eli the Iceman. So the way that you read this is, say here in Eli, the L means inductor. You should be using a V for voltage, but then you'd have to say Vli, the ikfamen, and that would be too hard to say. So you look at this, think EMF, and oh, that's a voltage, right? So the voltage leads the current. See, the voltage comes before current in Eli, so the voltage leads the current in an inductor. Similarly, if I go and look at ice here, the C is for capacitor. The I is for current. Again, the script E, it's EMF, but it's to remind us that's voltage. And here the current leads the voltage. Now, if you want to think about the other way, you can say the current lags the voltage because it comes in an inductor, or the voltage lags the current in a capacitor because that letter came second. So this is a mnemonic for how to remember the relative phase of voltage and current between inductors and capacitors. All right, so just to make this a little concrete, let's say I have a 20 millihenry inductor. And let's say I'm applying an external AC EMF whose maximum value is 10 volts. I would like to know the current, the maximum value of the current through the inductor if the circuit is being driven at 100 hertz. Okay, so my voltage across the inductor will be this EMF here. And since we're working in max values, we'll write max. This would equal IL max times the inductive reactance. So the current IL max will be the max voltage over the inductive reactance, which is the max voltage, over 2 pi FL, because that is the inductance. Now, this is one of those things when you're grinding this through your calculator, you want to be super duper careful. If you take a number and say you just hit divided by 2 pi, what you just do is you divide by 2 and then multiply by pi. So you're going to have to, take this number and then put all of these numbers in parentheses after the division sign to get it to work out right. So this will be 10 volts over 2 pi times 100 hertz times 0.02 henries, taking millihenries to henries, to get 0.8 amps max current. If you want the RMS values, you just go ahead and divide by the square root of 2. All right, so in the next video, we'll go ahead and take a look at LC circuits, and specifically, we'll look at one where there is no external EMF source. And then we'll go ahead and take a look, finally, at series circuits that have an external EMF source, a resistor, an inductor, and a capacitor. So we'll catch you over there.